Hello everyone, let's analyze. So today we're going to talk about the derivative of f as it maps domains in Rm to codomains in Rn. So that's going to be the subject of today's lecture. Now, to get into mappings from Rm to Rn, let's recall a little bit of the calculus of the derivative of f that maps open intervals in R to R. So just a quick calculus 1 review and some of the analysis behind it. So a little bit of real analysis 1 review. So if I have a graph of f and I want to know what the slope is at some value x naught, or what the derivative is at x naught, right? The derivative is the slope of the tangent line. Okay, we could actually express this tangent line as L of x equals f prime of x naught, right? Because L of x has the same slope of f at that point, times x minus x naught plus f of x naught. So the tangent line and f have the same slope at x naught. Well, another way of looking at that is, well, clearly because the L is tangential, L of x naught equals f of x naught, right? We get equality at that point because they're tangential, but L and f have the same slope at that point, which is to say they have the same rate of change, right? If someone runs at approximately the same speed as I and we start at the same time, then they will be close by. Now, of course, they only have the same rate of change here at this point, but the rate of change means their change is similar nearby. In other words, another feature of our tangent line is that L of x is approximately equal to f of x for x close to x naught. Okay, so this is an important feature. Of course, they intersect, but the fact that they have the same rate of change means that L of x and f of x are approximately the same if x is close enough to x naught. Now, we're going to make this precise using the definition of the limit. So we know that f prime of x naught is equal to the limit as x approaches x naught of f of x minus f of x naught divided by f of x naught. Put another way, the limit as x approaches x naught of f of x minus f of x naught divided by x minus x naught minus f prime of x naught. In other words, if I take this and subtract it to the other side, I get 0. I get 0. Also, I left a conspicuous space here. That's because I want to put everything over a common denominator. So if I multiply times x minus x naught and then divide by, I have my common denominator. Well, if we compare these terms to my tangent line, what I get is f of x minus L of x, And this is L of x divided by x minus x naught in the limit as x approaches x naught is equal to 0. What that means is, right, let's break out our epsilons and deltas. For any epsilon greater than 0, there exists a delta such that if x minus x naught is less than delta, and this is going to be what I mean when I say x close enough to x naught, specifically this. Okay, of course, inside of this approximately equal to is this epsilon. How approximately equal to? Well, this epsilon in this sense. Right? If this is true from this limit, f of x minus L of x divided by x minus x naught is less than epsilon. Or put another way, f of x minus L of x divided by x minus x naught is less than epsilon. Or put another way, f of x minus L of x is less than epsilon times x minus x naught. Okay, so for any epsilon I choose, I can guarantee that the difference between my function and my tangent line is less than epsilon times the difference of x minus x naught, so long as x and x naught are sufficiently close together, specifically less than delta. Since we're on the real line, this should just be an absolute value. So now we've made really precise what specifically I meant by my tangent line is approximately f of x if x is close enough to x naught, right? It's specifically this statement here. Now, let's return to my graph and the graph of the tangent line. We oftentimes call these functions linear functions, but that's not precisely right if we think of linear in the way we learned it in linear algebra. A linear function necessarily has to map 0 to 0. This is actually an affine function because its y-intercept or f-intercept is not 0. So it's a linear function, which is a scaling of x plus a constant. In this case, the constant would be the derivative times negative x naught plus f of x naught. That would be the constant. So the tangent line is an affine function. And we say that the derivative exists if the difference between my function and tangent line divided by x minus x naught is 0 and the limit as x approaches x naught. Right? This is essentially an equivalent way of defining the derivative. So now let's consider the multidimensional setting. F maps U and R M to Rn. The question we have is, for any epsilon greater than 0, does there exist a affine function L of x, which maps values of x near x naught to Rn such that f of x minus L of x is less than epsilon times x minus x naught. And here we're working with the Euclidean norm. So notice the similarity from this statement to this statement. Here, little l is the tangent line, and it's an affine function. The difference between f of x and the affine function is less than epsilon times the distance between x and x naught. I have the same thing here. The distance, using a norm as a matrix between f and an affine function, right? This should be my tangential affine function. This difference is less than epsilon times the distance between x and x naught. So does such a thing exist? Well, what does an affine function look like for an Rm to Rn? Well, an affine function looks like a linear function plus a constant. So a linear function from Rm to Rn can be represented by a matrix, right? And so because it's affine, it's a matrix plus a constant. Now remember, I need L of x naught to equal f of x naught. So if I evaluate at x naught, I need to get f of x naught. So let me subtract a times x naught and add f of x naught. And now I have, right, this satisfies L of x naught equals f of x naught, which must be true. This equals a times x minus x naught plus f of x naught. So here a plays the same role as the slope of the tangent line in the real line. So now that I have a representation for my affine function, let's continue this inequality here. So I can replace L of x with my representation for an affine function. This must be less than epsilon times the norm. Now, of course, I can divide through by x minus x naught. That'll cancel that. And if, for any epsilon, my affine function maps everything within delta of x naught in a way that satisfies this condition, right? This implies the limit as x approaches x naught of f of x minus f of x naught minus a times x naught divided by this norm is equal to 0. And if this limit exists for a linear mapping A, which is to say a matrix A, right? A linear mapping can always be represented by a matrix so long as I have a basis, and I do because I'm working in Rn and Rm. So we've now derived what it means for a multidimensional function to be differentiable. So let's put it all together in a definition. Let f map an open set U and Rm to Rn. And if for some x not in the domain, there's a linear mapping A such that, well, the change in f minus A times change in x divided by change in x is 0, and the limit as x goes to x naught, then we say f is differentiable at x naught. And the derivative is written df. Instead of f prime, when we're in one dimension, we write df because we're generalizing to higher dimensions. And of course, we're evaluating at x naught. So this is how we express the derivative. And the derivative is specifically the linear map A, which again, because we're mapping from Rm to Rn, A can be thought of as a matrix. Now I know what you're thinking. You're wondering, is the matrix unique? If f is differentiable at x naught, is the expression of the derivative as a linear map unique? Well, this theorem says it is, and let's prove the result. Suppose that the derivative is equal to a matrix A, and the derivative at x naught is equal to a matrix B. So let's consider the difference of B minus A times x minus x naught and norm divided by x minus x naught. So because the numerator and the denominator are norms, they are non-negative. So this quotient is non-negative. And now we can go about adding zeros. So let's add f of x minus f of x naught, and we'll subtract f of x and add f of x naught. We'll subtract a times x minus x naught. Of course, that's here. And we'll add b times x minus x naught. Divided by the norm of x minus x naught. So notice these numerators are equal because all I did is add and subtract f of x, add and subtract f of x naught. Now I can use the triangle inequality to say that this is less than or equal to f of x minus f of x naught minus a times x minus x naught plus f of x minus f of x naught plus b times x minus x naught divided by the norm x minus x naught divided by the norm of x minus x naught. Now, because I'm supposing that a is the derivative and b is the derivative, both of these terms go to 0 as x approaches x naught. Same thing with this term here. This goes to 0 as x approaches x naught, right? That's what it means for a and b to be the derivative of f at x naught. And because this is sandwiched between 0 and a function that converges to 0, that means this converges to 0. So therefore the limit as x approaches x naught of b minus a times x minus x naught divided by x minus x naught is equal to 0. Now notice that x is arbitrary. Well, let x therefore equal x naught plus alpha times v, where v is some arbitrary matrix. Well, if I let alpha go to 0, then that would mean x approaches x naught. So the limit as alpha goes to 0 of b minus a. Now notice x minus x naught for this x is just alpha v. And x minus x naught, alpha v. Now this equals the limit. And by the way, all of this is equal to 0 because this is true. Now remember, b and a are both linear operators, so this alpha can be factored out. And because I have a norm, I can factor out under an absolute value. Same thing over here. Well, now the only alpha present is here, and well, the norm of the absolute value of alpha divided by the absolute value of alpha is 1. So I get 0 is equal to b minus a times v, and the norm divided by the norm of v. Now v is arbitrary. Because b minus a maps any vector to 0, that implies b minus a is 0, or b is equal to a, and I have my uniqueness result. Okay, let's work out an example. Suppose f maps vectors in R2 to real numbers, given by this. F of x is equal to the norm squared. Let's show that f is differentiable at any point in R2, and the derivative is 2 times the transpose of that point. Now, suppose we didn't know that this would be the derivative. Right, it'd be straightforward just to drop this into the limit definition, show the limit is equal to 0. But let's try and give an idea of where this comes from. All right, we want to find a linear A that maps R2 to R, which is to say that I want A, or I can represent A by a matrix of size 1 by 2. So that at least gives us some sense of why I get the transpose of this vector. By the way, in my world, I like to always think of vectors in Rn as columns. I'm just partial to columns. So the limit as x approaches x naught of f of x minus f of x naught minus my linear mapping of the difference divided by the norm of the difference, that's equal to the limit as x approaches x naught. Okay, and now I'm going to do a little bit of rearranging here. Right, I know that the norm of x squared is x1 squared plus x2 squared. Right, so this is x naught 1 squared plus x naught 2 squared. So minus x naught 1 squared divided by the norm of x minus x naught. Okay, so I rearranged to have all the first entries here and the second entries here. Now why did I do that? Well, I wanted to give some intuition of where A11 and A22 comes from. Well, we know that if g of x1 equals x1 squared, then g prime of x1 equals 2x1. That means that the limit as x approaches x naught of x1 squared minus x naught 1 squared divided by x1 minus x naught equals 2 x naught. Right, because I'm taking the derivative specifically at x naught 1. That means the limit as x approaches x naught of x1 squared minus x naught 1 squared minus 2x naught 1 times x1 minus x naught divided by x1 minus x naught equals to 0. And notice that this numerator looks a lot like this term here, right? Divided by a first order difference divided by a first order difference. So this suggests that A11 is likely to equal 2 times x naught 1. And similarly, if I were to run the same experiment with g of x2 equals x2 squared, I would get the suggestion that A22 is 2 times the second entry of x naught. Okay, so now let's consider based on this suggestion, the idea that a is equal to 2x naught 1 to x naught 2, which is equal to 2x naught transpose. So now let's take this representation of a and plug it into our limit equation here to determine whether this is equal to 0. So let's continue this. The limit as x approaches x naught of x squared minus x naught squared minus, now I'm going to use a is equal to 2 x naught transpose x minus x naught divided by x minus x naught. Which is equal to the limit as x approaches x naught, which is equal to the limit as x approaches x naught of the norm of x squared. Now let's look ahead, shall we? Minus 2 x naught transpose x minus 2 x naught transpose x naught. Now x naught transpose x naught is just the norm of x naught squared. And this double negative means I'm adding 2 of these to this negative 1 of these. So I get plus x naught squared divided by x minus x naught. And now this looks an awful lot like the outcome of squaring something or foiling two of the same thing. In fact, it is. This is equal to x minus x naught squared. And then of course the numerator remains the same. Now I would encourage you to stop here and make sure that you understand why this numerator and this numerator are the same. X minus x naught squared is the inner product of x minus x naught and x minus x naught. If you were to carry out that inner product, you should get exactly this. So this cancels with the 2, right? I got 2 of them being multiplied divided by 1 of them. So 1 of them from the numerator cancels. Now in the limit as x approaches x naught of the norm, x minus x naught, well that's simply 0, right? So we've shown that, in fact, the differentiability condition is satisfied and the derivative is given by this. So it should be a familiar result from real analysis 1 that if a real valued function with a real domain is differentiable, then it's continuous. And the same thing occurs if I map Rm to Rn. If it's differentiable at a point, it's continuous at the point. And in fact, the proof is fairly similar. Right? I want to show that for any epsilon greater than 0, there exists a delta such that if x minus x naught is less than delta, then f of x minus f of x naught is less than epsilon, right? if I can show this, right, so this is my goal. Okay. So let's begin with such an epsilon. Let epsilon be positive. Then f of x minus f of x naught equals, and here's where I get to add and subtract some zeros. F of x minus f of x naught minus a times x minus x naught plus a times x minus x naught. And now I'm going to multiply by 1 in the sense that I'm going to multiply times x minus x naught and divide by x minus x naught. And this is less than or equal to, and here's where I'll use the triangle inequality. F of x minus f of x naught minus a times x minus x naught plus a times x minus x naught. Of course, we'll divide by x minus x naught. And here I don't need to divide because I already multiplied, so they cancel. And I get this. Now, if a is the derivative, at x naught, then this bracketed expression goes to 0 as x goes to x naught. Put another way, it's less than or equal to epsilon over 2 if x minus x naught is less than some delta. Now here a is linear, so as x minus x naught goes to 0, this also goes to 0. So this goes to 0 as x goes to x naught. Specifically, this is less than, sorry, not less than or equal to, just strictly less than epsilon over 2 if x minus x naught is less than some delta, we'll call it delta prime. Well, I claim we're finished because if x minus x naught is less than delta, which is defined to be the minimum of delta prime and delta double prime, then f of x minus f of x naught is less than epsilon over 2 plus epsilon over 2, which is of course epsilon, which is exactly what our goal was. So we've accomplished our goal, so we're done. So of course, in order to get a handle on what exactly these derivatives are, let's define the partial derivative. So f maps an open set in Rm to R, and x naught is in the domain. Well, then the partial derivative with respect to the jth coordinate at x naught is defined by this limit. Notice that this is the change in f as x naught moves in a particular direction, specifically the jth canonical direction, right? Divided by this change, which is measured by t. So if this limit exists, then that is the partial derivative of f with respect to the jth variable x, evaluated at x naught. So let's work out an example. Let's consider f of x is equal to the norm of x squared, which is an example we've already looked at. Then if the first partial derivative exists, at x naught, it's equal to the limit as t goes to 0 of x naught plus t e1 squared minus x naught squared divided by t, which equals the limit. Again, the same limit holds. We need to figure out what that is. Well, that's each of the entries squared. So this is x naught 1 plus t squared plus x naught comma 2 squared minus x naught comma 1 squared minus x naught comma 2 squared. Of course, this term cancels with this term. Divided by t. I get the limit as t goes to 0. X naught 1 squared plus 2 x naught comma 1 t plus t squared minus x naught comma 1 squared divided by t, and now we can cancel. So this term and this term cancel. This t will cancel this and this. And now as I take the limit as t goes to 0, well, this t term goes to 0. And I get 2 x naught comma 1. And similarly, the derivative of f with respect to x2 at x naught equals 2 x naught comma 2, and it would be a good exercise to show that, to recreate these steps, but taking the partial derivative in the second direction. So if a function is differentiable, we can actually use the partial derivatives to make the entries of our derivative matrix. So let's prove this statement. Well, the fact that f is differentiable means that the limit as x approaches x naught of f of x minus f of x naught minus my derivative evaluated at x naught times x minus x naught divided by the norm is equal to 0, right? That's what it means for a function to be differentiable. Now, right, x is arbitrary, it just has to converge to x naught, so let's let x equal x naught plus t times ej. Then I can replace these x's with this representation and take the limit as t goes to 0, because as t goes to 0, x approaches x naught. So I get 0 is equal to the limit as t approaches 0 of f of x naught plus t times ej minus f of x naught minus d f of x naught. Now, of course, if this is x and I subtract x naught, I'm just left with t times ej. Now divided by t, because x minus x naught is t times ej, and the norm of that would just be, well, the absolute value of t times the norm of ej, which is 1. Now notice this term here is equal to t times the jth column of my matrix. So I know that for y in Rn, yk is less than or equal to the norm of y, and that's true no matter which entry I choose from 1 through n. And you should be able to prove this, by the way. Now, this is a vector in Rn, as is this, and this is also a vector because it's the jth column, right? So it's a vector in Rn as well. It's a column vector times t. So in fact, I could take the kth entry of this, which would be given here, the kth entry of f at x naught plus t ej, minus the kth entry of f, minus the kth entry of the jth column, right, which is the kj entry of my matrix, times t, divided by t. This numerator is less than or equal to this numerator because this is just this norm, divided by the absolute value of t. Now, I know from here that this converges to 0 as t converges to 0. Therefore, this limit, that is this, must also converge to 0. And because it converges to 0, I can drop the absolute value. And because this converges to 0, I can take this term and add it to the other side. When I do, these t's would cancel. And I get that this limit, which is exactly the definition of the derivative of the partial derivative of fk with respect to xj, is equal to the kj entry of my derivative matrix, which is precisely what we wanted to show. So we know that if the derivative of a multidimensional function exists, then the partial derivatives exist. And in fact, the entries of the derivative, which is uniquely determined, are given by the partial derivatives. So, is it enough for the partial derivatives to exist to say that the derivative exists? And unfortunately, the answer is no. We need a little bit more. Specifically, we need f to be continuous, and we need the partial derivatives to be continuous. Then we can say the derivative exists. Okay? The proof is a bit long, but it's in your book, so we'll omit it for now. Now, let's define the gradient. The gradient is probably something you're familiar with when you took vector calculus. Of course, it's pretty useful in all types of physical and engineering applications. So let f be open, have an open domain, let it be differentiable at x naught. Then the gradient is a vector whose entries are all the partial derivatives of f with respect to each component of x. And in fact, we can really think of this as a list of slopes of the tangent Now, what's the right word? It's not a tangent line because this is in multiple dimensions. We can't exactly say a tangent plane because m could be bigger than 2. What we really mean is a hyperplane. In other words, a hyperplane is something that exists in a dimension 1 less. The list of slopes of the tangent hyperplane. To graph of x, f of x, of course tangential at x naught, and each canonical direction. Now we know that if a function is differentiable, and if a function maps Rm to R, then these list of partial derivatives in fact make up the derivative matrix. So for such a function, the derivative matrix is just the transpose of the gradient. Or, put another way, for any vector in Rm, if we think of the derivative as a linear operator, the linear operator applied to V is the gradient transpose V, which, right, in Rn we know is just the inner product of the gradient and V. Now, as we just mentioned, the entries of the gradient, the partial derivatives, are a rate of change or a slope of f as x moves in the ek direction. But what if x moves in a different direction? What is the rate of change of f in an arbitrary direction of the change in x? Well, that's given by the directional derivative, which is precisely that. If f maps to R, x naught is in the domain, and v is a unit vector. Of course, we don't want its size to pollute what we think our rate of change is, so we just keep unit vectors. Then the rate of change of f, specifically as x moves in the v direction, is given by the directional derivative. And it's defined, well, very similar to how we define a partial derivative, but instead of going in a canonical basis direction like ek, we're going in the direction of v. Otherwise, the definition is exactly the same, and we use this notation to express it. By the way, the directional derivative and the direction of ek is just the partial derivative with respect to xk. So how does a directional derivative relate to the derivative? Right? Typically we think of derivative as a way of describing a rate of change. So how can I connect the derivative to a rate of change, but specifically in the v direction? Well, the directional derivative, or the rate of change of f in the direction of v, is just the derivative times v, right? Or applied to v if we think of it as a linear operator or a linear transformation. So this is true for any unit vector v. By the way, just as a review of last lecture, a unit vector v is literally on the boundary of the open ball centered at 0 with radius 1. So that statement should make sense to you. So let's prove this. Let's let x be a shift from x naught, so that we can put it into the format of our definition of directional derivative. Then the limit, right, of f of x, which is this, minus f of x naught, minus the derivative at x naught, times x, which is this, minus x naught, so I would just get TV. Now remember, f here is real valued, so it's just an absolute value, divided by the norm of TV. This is equal to 0. How do I know this is equal to 0? Well, because that's the definition of differentiability. Now, I'm taking the limit as x goes to x naught, but that's the same thing as taking the limit as t goes to 0. Now, notice that this is equal to the absolute value of t times the norm of v, but the norm of v is 1 because v is a unit vector. So the limit as t approaches 0, x naught plus tv minus f of x naught divided by t minus df of x naught. Now this t and this t are going to cancel, so I just get v this is equal to 0. Now because there's no t here, I can distribute this limit. And of course the limit of this is, by definition, the directional derivative. Right? So this limit is the directional derivative. So the directional derivative minus the derivative is 0. So I can conclude the directional derivative is the derivative times v. Now, by the way, as a corollary, the directional derivative, if I use the fact that these real valued functions have as their derivative matrix the gradient transpose, that means the directional derivative is the gradient transpose times v, which is the inner product of the gradient and v. Now, let's get one more result about this directional derivative. So let f map an open domain in Rm to R be differentiable. Then the direction of steepest ascent at x naught is given by the normalized gradient. So let's prove this. Well, we just showed that the directional derivative for any v is given by the inner product of the gradient and v, which is equal to the norms of each times the cosine of the angle between them. So theta here is the angle between the gradient and v. Now, this is 1 by definition of a directional derivative. So if this gives me my directional derivative or slope in according to a particular direction, when is this maximized? Well, the gradient at a point is the gradient, right? There's no choice of v that's going to change what the gradient is. But cosine of theta can be maximized. Cosine of theta is maximized when it's 1. All right, so this is maximal when cosine of theta equals 1 or theta equals to 0. So if the angle between v and the gradient is 0, that means v and the gradient point in the same direction. So that implies that v is just the normalization of the gradient. Now it also implies that the norm of the gradient is equal to the steepest slope. At x naught. And in fact, this concept of steepest slope and steepest ascent is still used by mathematicians who study optimization as an iterative method to ascend to a maximum or descend to a minimum of functions. Well, that's it for today.